Okay, good evening, everyone, and we are delighted to have Dr. Omid again. Today, Dr. Omid will go through those XYZ, and hopefully, if we have time, he would maybe give a brief overview regarding the beam. So, Dr. Omid, the floor is yours.
Good evening, everyone. I was muted, sorry. Today, I might have a change of, it depends on how you feel. So let me ask you, should I go through over those XYZ again, or should I spend time on the BEAMnrc? If you feel we should do those XYZ again, we will do that, but then we can postpone BEAM to next week. So but just by raise of hands, what do you think? Should we go through over those XYZ again?
Not the yes, it's just the raise hand, please. Just raise up your hand so we know the number of people who would like to go through those XYZ.
Okay, so we have 5. Okay.
Yeah, most of the people I see. Yeah.
Yes. Okay. Okay, we'll do that. I wanted to move forward with BEAM, but that's fine. Okay, so those XYZ is a user code similar to those RZ, but now the geometry is not an RZ geometry, but it's an XYZ geometry. Think of a CT. A CT, we have voxels, and it's an XYZ geometry. We have usually a CT will come with a 512, 512, and then we have the number of slides. So those XYZ is basically a phantom where we have an XYZ geometry. You will see we will use actually this phantom not in just calculating distributions to patient and so on, but actually when we want to optimize or tweak our BEAM model. So when we go through BEAM, that I will discuss that more. So the geometry is an XYZ geometry. You can use it to calculate PDDs as well as profiles. With the dose RZ, we said that we were limited only to probably just calculating doses across the beam central axis because the rest are rings. And usually we don't see, I mean, at least from my interest to calculate profiles and so on, that's not, I cannot use the RZ geometry to calculate profiles, but I can do this with the dose XYZ geometry user code. Okay, so let's start. Okay, and I hope if people, you actually have your computers aside, you can actually do this with me. So it's like a practice to all of you. So I've just opened those XYZ short. So this is the graphical user interface, the GUI. And what I want to do is start a new input file. So let's start a new input file. I'm going to select a PEGS data file. The one I have is called Phantom. Okay. And then click on OK. So now I get this window. I can put a title. What should we do? Should we do 12 MeV electrons or do you want photon beams? Doesn't matter. I mean, okay, let's do electrons. Since last time we did a photon cobalt, we will do an electron beam. So title, I'm going to call this probably 12 MeV electrons. Okay, and probably we want to define. We're going to call it a 10 by 10 field. Okay. So we will go from top to bottom. The first part is to define the phantom. Those are Z. I spent a lot of time in defining the phantom, the slabs and the rings, as well as to assign medium. Also, this is the same case for those X, Y, Z. So just 1 minute, please. Okay. Can you see the screen, or did I lose the sharing?
Yeah, we can see the screen. Now we lost it.
Okay, I'm going to share it again. So,
now we can see. Okay.
Okay. So now the phantom definition, again, we're going to define the geometry is an XYZ geometry, but what we need to define is the boundaries or number of voxels and the size of the voxels and so on. That's the geometry. And then the next step is to assign medium to these voxels. We're not doing CT data. We're going to start with non-CT data, and we're going to define the phantom using, these are the voxel dimensions. There are two ways to define the voxel dimensions. Individual is we set the boundary. So for example, we're going to put a -40, -39, -38, -37, and so on and so on. Okay, it's like what we have done with the planar in the RZ. So there you can have set things where we define distances of these boundaries, or as group. This is what we're going to do. It's actually faster. Group to define the group thicknesses. That's basically how we're going to do this. So I'm going to use 3 groups for the following reason. Okay. So the first group, think of your phantom. So now we're moving from the from one side of the phantom to the other side. I want to have a finer resolution of voxels in the middle where the beam is actually going to incident. But then at the sides of the phantom, I want to have larger voxels, or maybe just one even dimension, so that, just to provide scattering. So the first group, this is the width of the voxels there. Let's put them as 1 centimeter. And suppose I'm going to put 5. So I have 5. And then since I'm talking now in the middle, I'm going to put, let's say 0.25. That's 2.5. And I want to actually use this across, since I'm looking at a 10 by 10 field. So I have 10 centimeter. So I need 40. But we also want to go beyond, more than 40. So let's use 60. Okay. So 60 times 0.25, that's, I think, that's 15 centimeter. Should we use 80? We can do 80. So this is actually 20 centimeters now. So we have 5 centimeters, and then we have 20, and then I'm going to finish this by another 5. Okay. So the total, now we have 20 and 5, we have a 30 centimeter phantom. You can increase the number. I think the limit is, for the default is 128, if I'm not mistaken. The number of boundaries or voxels in one dimension, in the X dimension. So we are still okay. We're still fine. I could even put here to reduce this, for example, to 0.2, and then increase this to 100. That's still fine. So the maximum, it says that the maximum X boundary is 30 centimeter, because if I did not put any number here, that means the phantom is starting at 0. But we want 0 is the center of the beam. So I want to actually shift the phantom. So I'm going to put this as -15. So when I put -15, then the maximum boundary is 15 centimeters. Okay. So this is for the X. Now for the Y, probably I want to have the same resolution or voxels. So this is going to be -15. And then here the width is 1 centimeter. We have 5. We said this is 0.2. 100. And then I have 5, 1 and 5. So the, sorry. Okay. So the total number of voxels, that's important to know. So we have 110 voxels in the X and Y. Now in the Z direction, I'm going to use group. Okay. So we have done an example with those RZ. Should we do something similar? Maybe we can do that. I'll put 2 groups. So for the Z, I wanted to actually, the minimum, I wanted to start from 0 because that's the surface of my phantom. And then we're going to have a 0.1 of 100. So 12 MeV, the range is going to be 6. This is more than enough. And then if you want, we can do 1 centimeter. I have 10. Okay. So the total number of voxels is still 110. This is not necessary, but I'm just showing you what you could do. So the maximum Z boundary is 20 centimeter, which is enough for the 12 MeV electrons. Okay. Once we have done that, the next step is now we need to define the media. Okay. We now need to assign media to voxels. Since in this example, I want to fill all the voxels with then the number of media, I'm going to put them as 1. But if you want to have to do something fancy, for example, have some voxels to be assigned with bone or with air or something, then increase, the number of media. So we're going to put 1, leave it as 1. Define media. Okay, the first media. So I have here 5 H2O, 5 to 1 isoario. Okay. Let's put 2 so that you see what happens. Okay, so I'm going to put 2 here. If my media, now suppose I want to actually put this to be air. Okay. Or lung, let's put lung. Or bone. Okay, yeah. So the next step, okay, now I've selected the medium 2, but now I need to set the voxels, the medium to the voxels. So we're going to do, we'll set it to the voxels. Remember, we had 110 voxels. So for this goes from 1 to 110. Y is also 1 to 110. I think Z, we also set it 1 to 110. We have 110. Okay. And that's the medium. So we're going to put water there. Now, this density option, this is relevant when you're trying to do something, do a comparison with treatment planning systems. Treatment planning systems, they give you those in water, even in heterogeneous, even if you turn heterogeneity on, still the doses are reported as dose to water. But what happens is that based on the CT numbers, then they change the density of the waters and so on. So for example, if you want to override the default density of water in the PEGS data file, you can write the new value here. But it's 1. I'm going to leave it as is because it is then going to grab the density, the default density in the file. So suppose we actually want to actually have a layer of let's say bone. Okay. So now I'm going to add another group. Okay. And suppose the bone, bone, I'm going to put 1 centimeter, and 1 centimeter will start at 1 centimeter depth. Okay, that's simple. So 1 centimeter depth, I know that the first 10 voxels, this is going to remain the same. because I want it on all across the X, Y, Z direction. Okay, but from the Z, I'm going to put 11 because the first 10, because the first 10 voxels, the resolution or is 1 millimeter. So number 11, voxel number 11 should be at 1 centimeter, starting from 1 centimeter, and this will go up to 20. And I can put here bone. Okay, is this clear to everyone?
Please
okay.
raise your hand if it is clear for you.
Okay. Hey, but انت دايما you always give me trouble. Okay. I tried to make the font larger this time.
Okay, I think it's fine. Go ahead.
Okay. So please interrupt me. I mean, whenever Bilal is following, you know, the participants. So if there is, you have a question, just raise your hand and Bilal will give the chance to interrupt me. Don't worry about that. Okay.
Dr. Wamid, can you raise up your voice a little bit because
it's still bad. How about now?
Yeah, now it's okay.
Now it's okay. Okay.
Yeah, and can you explain the bone as well?
Explain. Okay. So again, that's okay. Let's do something. Okay. So think of, now I'm just going to draw something on the Z direction. Okay, so we have these slabs. Right? Okay, so each one is 1 millimeter. My drawing is bad, but you know, just bear with me. We said in the problem to actually insert bone in my phantom, starting from 1 centimeter depth up to, and the thickness of it is going to be 1 centimeter. So it should go from 1 centimeter up to 2 centimeter depth. The phantom, when we constructed the phantom, we have made, let's go back. So it's in the Z direction, okay? So the voxels, you see, I set 100 to be 0.1. So we have 100 layers of 0.1 centimeter thickness, and then I have 10 with 1 centimeter thickness. So the voxel that is at 1 centimeter depth is going to be voxel number 11, right? And the voxel that is just before the 2 centimeter depth is going to be voxel number 20. Yes, you have a question?
Yes, speak up, please, if you have any questions.
Hello.
Yes.
Yeah, sir, I can't use the media because there is an error telling that there is no unmade file.
Maybe they have something wrong in the PEX data. That's something we can fix later. Okay, but I'm talking now about what I'm doing. Is it clear or not clear? That is something particular to your installation problem. Okay? Okay. So voxel. So now when I define the media, these are my two media. I'm going to set the media, and like in the RZ geometry, we said the application reads line by line. So it's going to first execute this line. The execution of this line will fill all the voxels in the phantom to be water. And then it's going to execute this line, and it's only going to fill the voxels that are between Z, which have Z 11 up to 20 with bone. If we reverse sequence, I will always get water. Okay, so be careful about how you fill your geometry. Here, for example, suppose I don't want the full slab. Suppose I want to actually have a small, let's think about it. So let's suppose I have a 2 centimeter bone in the X and Y direction, okay? So now I have to figure out from which voxel we should start. This is 110, so the middle of it is going to be 55. 55 is at 0, okay? So from this side, we need to actually, so if we said 2 centimeters, that's going to be, remember, these are 0.2 millimeters. So I need 10. So this will start from 46, I think, up to 55. And no, we need to actually go to the other side. So 55 plus, we have two times, so 20, 65, 75. There is some 2 centimeters, yeah, 1 centimeter. So this is 65. Does this make sense or not? Let me think about it. 55, this is 2 centimeters from here. Yes, and we need 2 centimeters from there. That's going to be 65. Okay, so now actually the dimension of the bone based on this is 4 centimeters. I'm going from minus 2 centimeters up to 2 centimeters. So it is 4 centimeters. Okay, and if I wanted this one to be, let's say 1 centimeter in the Y direction, then we have to do up to 60. Okay. So it's a bit tricky. I mean, you know, sometimes I get confused doing it, but you really have to think of where is my voxel. So I believe this probably will give me in the X direction a 4 centimeter wide bone, and in the Y direction, I'm going to have a 2 centimeter wide bone. And in the Z direction, it's going to be 1 centimeter. Okay. So I'm just showing you an example. Maybe I'm missing one or two voxels, but this is an example of how you would actually insert a certain inhomogeneity in the medium. Okay. So the ones we're set. Okay. Now, so we finished from the phantom definition. The next step is to select our source. So our source is going to be an electron beam. And then the source type, since it's a 10 by 10, I'm going to use a parallel beam with a rectangular collimator. Okay, parallel beam, yeah, this one. So when I open that, this tells me, so the X and Y, Z of the isocenter, think now we're going to put the phantom at isocenter. So that is 0, 0, 0. So this is the coordinate of isocenter in the phantom. Okay. And then theta degrees. Okay, this always confuses me. I'm going to hit rectangular beam. Okay, so this is your phantom X, Y, Z, and the theta and phi degrees are angles. So the phi is this angle, like that, and the theta is this angle going from down to. So when theta is 0, this is shooting upwards. So this is your source. Think of this source, and this is the theta. So when theta is 0, that means this yellow source is going to come from down, but we want it to be the opposite. We want it to come from on top. So theta has to be 180. Here. This is in degrees. And the phi is just collimator rotation. I don't care about that. That I can put it to be 0. Okay, monoenergetic. The kinetic energy is 12 MeV. Okay, and the total beam width, this is going to be 10, and this is 10, and this is collimator is 0. Okay. And you can read actually here, the position of the beam collimator is defined using the angles theta and phi. Phi is the angle between the positive z direction. Positive z is downwards. And the line joining the center of the beam, where it strikes the phantom surface to the eye center. In a polar coordinate system, this angle is known as the polar angle and normally has a range between 0 and 80. Note that a center beam incident along the positive x-axis has theta equals to 180, as I explained to you. This is your theta. It shows from here. This is the angle theta. Okay. So that's it. We can hit on OK. So we finished defining our source. Then the last step, or this is the simulation parameters. This, as I told you, that's 500, since we're not going to control the simulation by time, but by particles. And I'm just going to do 10,000 here. The run option, this is first time. Okay. These, when we do some other select different sources, we will have actually an option to fill the medium surrounding the phantom. So for example, if you have water, for whatever reason, you want to fill the medium beyond the phantom. Our phantom has a dimension of 30, 30, and 20. So if you want to fill medium there, then we can actually fill it from here. So it's a phantom there, okay? And this option is also is good to understand. How far less, when the Monte Carlo simulation runs, what happens is when your electron the simulation moves it, let's say a certain distance, it will check, is this electron going to go to another voxel or not? Because if it's going to another voxel, that voxel could be a different medium, and the physics then that there might be an error there. So what happens is, if it's going to move to another voxel, it moves the electron to the boundary first, and then physics simulates some physics as it's entering the new voxel. But this, if our phantom was, everything was water, this you can actually turn it to be on. So how far less is basically, how far less, don't ask, just move the electron, move it. Don't ask where the boundary is. But since we have a heterogeneity of bone inside our phantom, then we actually, we need to have better or more accurate simulation. We need to turn it off. We need, to take care of these boundaries. And the difference is that it can actually improve or reduce the time of simulation. So that's the main reason. Okay. Are there any questions?
Yes, there is a question. If we make theta 0 and x is the depth, is it the same result?
What's that?
If we make theta equal to 0 and x is the depth, it will give us the same result?
Here, okay, let me see what, okay. So where is x? X is not here. I don't see x or the depth. This is my phantom. My center is here on the surface. Okay. So I want the source to come from this direction. I want it to come from top to shoot to bottom.
Yes.
Okay. So if this is from the bottom, then the particles are shooting this way. So actually, if we do that, what's being suggested, this is actually going to be at the epicenter, but the particles are going to be emitted there outside, not in the phantom. So even like this source is not going to enter the phantom, because the source position is going to be at epicenter, which is here. Okay, the surface, and the particles are going to be emitted in that direction. So that's why we need to flip it. We need to make the source to come to have a 180, so that particles are emitted in the lower in this direction. So I don't think what's been suggested actually will, but I could be mistaken. You just enter and see if you get the dose or not. And does it make sense or not? Okay. Any other questions?
No, we don't have. Go ahead.
If we make the theta 0 and x is the depth, okay, we don't have x, it's a z. Okay. So the next, so here we have finished this part, simulation parameters. The last thing we need to take care of is the physics part. Okay, so that's the EGS parameter. Okay. So this is now because I started, it seems that with those X, Y, Z, the default is actually, it uses old physics. Okay. So this, we need to change it to exact. But just look at, there are three things. We have to just make sure we're doing exact, this boundary crossing algorithm. These settings are for all simulations. So when we do beam simulation, when we do those RZ, you check the physics, you check what's on or off. Electron step algorithm, I think Presta 2 is correct. It's the later one, Presta 1, Presta 2. And the spin effects, it has to be on. Okay. Now the rest, it's up to you, optional. So Rayleigh scattering, do you think we should actually turn on Rayleigh scattering for our simulation? Because that means it's just going to take a little bit more time. Okay. You can if you want. Bound Compton scattering, do we want to, because it's based on Klein-Shina, assuming electrons are free, but electrons are not free. And that has an effect at low energies. So usually when you have low energy simulations, we probably want to turn on Rayleigh scattering. We want to turn on bound Compton. In our case, maybe we can leave them off, but it's up to you. But we can just turn them off. I personally like to just use the best thing, although I know that it does not have an effect. And usually I run my simulations on powerful machines. But if you're struggling, you want to save a bit of time, then you have to think of this physics. Atomic relaxation, do we want characteristic X-rays to be produced or not? So, can turn it on or off. Does it matter for our simulation? It does not matter. I totally agree, it does not matter. But it's an option that, you know. So these are physics, okay? Brownish angle, and there is the, where is the photo effect, angular. So all of these are physics options, and you can just hit on the help. And sometimes they guide you. They tell you, look, this is probably important when we're doing low energy or when we're doing high energies and so on, okay? But it's up to you. I leave this to you, okay? But these three are very, very important. Okay. So now we have done.
We have one question before you go to the next step. Can you please explain the utility of range rejection?
You ignore that because that's why we're using the modern physics in EGS.
Okay.
Okay. If you're going to use the older one, the Presta one, and so on, you need to figure out what's this range. I personally don't know what they mean, because they were used in older simulations. Okay, so you don't have to worry about it. But go and click the help button and read about it. So once we have done this, okay, we close, and now we're going to save the file. So we're going to save the input parameter. So I'm going to call it depth dose, although it's not a depth dose, it's actually a full phantom simulation. 9, this is 12 MeV. Okay. And I have water, and I'm going to put bone because I know it has water and bone. Okay. Okay, one more thing is in the parameters. EGS has an application. It's called dose XYZ view. I don't think there is, I don't see a shortcut for it here, but I will show you how to launch it, not a problem. Now for dose XYZ view, it's a viewer, okay, for distributions. In order for it to work, we need to know the doses in the different voxels, but we also need to know what's the medium in it. So it actually needs a separate file where it actually reads the medium or something, you know, for the boxes. So for that one, here we need to actually include output That's the exFAT data file. Okay, so that is important because if this was turned off, we cannot actually use or view the dose distribution with those XYZ. Sorry, with those XYZ show. We can still do stat dose, we can get the profiles, but we cannot use that application to read the or to for the dose XYZ to display the dose distribution. This is irrelevant, I think. Define groups of voxels. This is something in the output file. Okay, so this is not relevant to this. This is basically in the log file of the output. If you want to actually list the doses there, so we're gonna keep that. We're not gonna use it. So file. Okay, close this. So I'm gonna save. And now I can run, just make sure that I know the dose XYZ is compiled. So I'm going to run it. And we're going to execute. Okay? So it's now executing. This is 10,000 particles, electrons. If your simulation goes very fast, probably there is something wrong. One of the issues could be that the source is actually, you did not put the source correctly. So you put a 0, 0. So the particles are shooting away from the phantom. That could be a reason. Okay. So I have done this simulation. So let's look at some of the statistics. So it's number of charged particles. I'd like to look at this number. So I can do 1.5 million histories per hour. And this is on one CPU. I have 8 cores. So I can do 1.5 times 8. So I can do 12 million in an hour. So in 10 hours, I can do 120 million histories. Okay, so that's how I calculate the time. If I launch something today and I want it to be ready by tomorrow morning, okay, I'll be 12 hours. I know, for example, 1 million today now, I know that by tomorrow morning, this is not going to be done. Okay. And what you do is you start, you do, like in my case, I would do 100 million. By tomorrow morning, I would come and check and look at the statistics, the standard deviations. Do they look okay, or I need to improve on that? Okay, depends on the application that you want. Okay, so this is done. Okay. Now, the data. So let's look at everything now. It's because now we're dealing with those XYZ application. So everything is going to be stored in your exome under those XYZ. Now, if I do ls minus LA, okay, or dir in Windows, or actually with Windows, you can do this, browse through the file, your Finder, graphical user interface. Where is my file? Okay, so they are here. So this is the cobalt. I did this last week, and today we did this, the 12 MeV water. So we have a bunch of files. This is the phantom file. Okay, remember when we click that option, it generated this phantom file, and you can see the size is actually big. In Linux we can add H, so the whatever in human readable they call it. So when I do with H, now I can see the sizes of the data files. So the phantom is actually 35 megs, and the 3D dose is probably double that. Why it's double? Because we have values of the doses, but also values of the standard deviation. So we have, for each voxel, we need to record 2 things probably, dose and standard deviation. It's actually records something else, but just so that you understand the data stored is the dose, it's more, not just the dose. Okay, we have a question.
I have a question. why we have left the
zero.
max
It's
Z
zero.
boundary in empty.
Yeah, it's 0 by default. You can
Okay.
put 0 or leave it empty. Okay. Okay. So that's the phantom, and I can show you actually what is there. So those 12, okay, and then we have X phantom. Okay, you see a bunch of numbers. If someone knows how to decode this, that's excellent. But it's just and you can tell that this is something related to the phantom because at the beginning, 2, that's 2 medium. This is the first medium, and this is the second medium. But then the rest is, it has the boundaries probably, where is the X boundaries of the boxes, and also probably the mass or something there, okay? So you don't need to worry about this, but I'm just showing you the files, so ls minus lah, and then I'll put so that it only lists those. Okay. So that's one file, the phantom file. The input file is the file that we actually generated now. So if we look at it, those 12, okay. Okay. You will find it's a text file and bunch of numbers. Okay. As you become more experienced, and if you want to use the voxel, the terminal, then you probably will start to understand what's there in the file. I'll just show an example. So for example, I can come here and change the second medium. Instead of bone, I can put lung. Okay, so I can just do it directly from here instead of opening the GUI. I can, for example, increase the number. So instead of this is, I know this is 10,000, 20,000 is the number of particles. But if you want to restart, then this option has to be 1. So when you select the restart option, it's basically in the input file, this is going to be 1, not 0, and so on. So with time, you will, if you want to use the terminal, you will start to understand time, triplet option. That is something that is not an option available on the GUI, unfortunately. So you type it here, and when you run the application, it will run with the physics that triplet production is on. Okay. So that is the input file. Then what we have is the xdat file. Okay. That I'm not sure what's in there, the xdat file. Okay. This is, okay, I don't know what's there. Okay. And we have the list file. Okay. The list file is just a summary of what has been done. So just put something in a text, because this is how they viewed the results in the past. So it shows you, okay, this is the summary or a log of the simulation. These are the boundaries for the X, Y, Z groups, and probably it has the medium somewhere. This is the physics part that was used, okay, and how many histories simulated for this run. So it's 10,000 histories to be analyzed, and this is the result, and so on. It's the log file that we have. So those X, Y, Z. Let's do something here, 12 MEV. And about, so now remember, I changed in the input file something so that it restarts. Okay, I could do this from the GUI. Okay, I'm not challenging you, but just showing you if you can do it faster way. So now I did restart, and we actually add 20,000. So it read, it's a restart option. It has to make sure that previous data is available, and that's in the 3D dose. So it went and read that. If that file wasn't there, it will tell you error. I cannot restart. Start from where. So at the end, we now have ran the simulation now for 30,000. 10,000 before this run, and this run is another 20,000. Okay. Errors, if there are errors in the simulation, okay, one thing you can look into is the errors file. So we can go and, for example, see what's there. Probably there is nothing. Okay, just ignore output. Okay, so everything is fine. But if there was an error for some reason, then it will log it here. It will tell you where is your error. Medium is not present. You're trying to restart, but we cannot read something. Maybe it will be listed there. Okay, so the last thing is now we have the data. I showed you the 3D dose data file, but that is very difficult to decipher. I want to actually extract profiles. I want to get the PDD. For that, we have to use an application. It's called StatDose. Okay, so I'm still in the dose XYZ directory. I type stat dose. Okay, and it's not a graphical user interface. It doesn't have a graphical user interface. It has to be done through terminal. So stat dose, when I launch it, start it, I get this menu. Now, the first thing we need to do is to read the dose distribution. So I'm going to do 1, okay? And in that folder, in the dose XYZ, I have an old DD cobalt water, DD 9 MeV water, and DD 12 MeV that we ran today. That's the advantage of choosing a good name. If you put, for example, Phantom 1, Phantom 2, Phantom 3, you would not know what's there in the Phantom or what's the energy and so on. So basically the Phantom, and as well as what's your source. That's probably what you need to do. So we're going to do 1. I want to read that data. So that once we read it, we put it in a temporary storage in the application. So that's one. Because you can read multiple files. You can read one file. I can go and read back again. For example, number 2. Let's do this. So read it, and then I'm going to put it now in a different storage file. So 1 was the 12 MeV storage file. 2 is on the MeV. And now I want to exit. For example, you can do some statistical analysis. I mean, you can actually have these two dose distributions. I think it's not going to work because the number of voxels are not the same in the geometry. But for example, suppose we ran two simulations with the same voxel geometries and so on. Probably we can do something, do some statistical analysis. So when I do this, I can get the difference between the doses, something like that. Okay, I haven't done it personally. Okay, but that's something, an option that you can do to analyze, subtract two this. Like now, if I try to do it, I think I will get something wrong. Okay, binning structures incompatible, because the first one, I think I used 84. The second file, the one I did today, is 110. So that's why it's not going to work there. So let's go back. I could normalize if I want. So for example, I can select 3, okay, and I can normalize probably to the maximum along the beam central axis, or normalize the dose to a specific voxel. For example, if you want to normalize your dose to a depth of 10, then you need to know the voxel depth of 10. It should have a number, or a, I don't know. Probably you can specify the coordinate. You can normalize to the average dose. You can apply a scaling factor or denormalize it. If you have something normalized, you can denormalize it. So I'm not going to normalize. I'm going to use 0. Rebinning, we had, remember, different bin sizes. We had, for example, 1 millimeter in the Z direction, 1 millimeter, 100, and then we had 10 of 1 centimeter. If I want to change this to, for example, just make 2 millimeters all across, I can do it from here. Okay, just so that it makes plots, with equal binning of, whatever. But the last thing that's important is to plot 5. So there I want to plot. I don't want to do comparison. Let's try comparison plot. Axis for comparing. So we're going to do, so I want to compare the PDDs. This is the first time I'm trying this option, by the way. So we'll see. So PDDs, I'm going to do the comparison along the Z axis. So 3, coordinate 0 and 0. Okay. Fine. Let's keep this as 9. So input curve number to be plotted. So I'm going to, that's for the 12. And then 2. So we put 1 and 2. And now I'm going to click 0 to view the graph. Okay. So this is the graph of, I think probably that is a misnaming. No, maybe it's correct. No, I think that's not MeV. Yeah, true. So probably the 12 MeV is the water bone. Oh yeah, I forgot because we have bone. The statistics are bad. So basically, I need to run this for more particles. But you can see here the red curve is actually the 9 MeV curve. That I think I ran for 300,000 or something like that. I forgot the number. And I use paraprocessing. Okay. If you want a profile, then by the way, for Windows, you know, this is not going to work. It's going to generate the file. The file will be saved with this name. Let me show you. So the output file, probably there is a file now in the directory. So let's look at it. So ls minus la 12 MeV. Oh, no, it has a different name. LS. Okay, so we should have a file called compare plot, because here we have is I just use the default, and the default was to call this the output file compare plot this here. So you can, for example, put the name, and when it comes to actually showing this graph, this is not going to work on Windows. The application cannot launch Qt Grace automatically, but it will save the file. All what you need to do is you go to your file finder, go to the file, drag it to the shortcut of Qt Grace, and you will get your plot. Okay. Okay. So let's do profiles. Start those. Okay. So we're going to read again, because I quit the application. That's why I have to read again. I'm going to read just, no, this is bad. The profile is bad. I need more statistics, but I will look for number 2. Find number of temporary storage. Okay, that will be 1. Okay, it ran the voxels. Then we're going to exit. And now I just want to plot the profile, plot profiles, number of file profiles. Okay, 1. Okay, now the profile. In which axis do I want to plot it? I don't want depth. I want of axis profile. So I can select either across the X or across the Y. So let's select across the X. And graph title, that is fine. Output name, I will leave the default. Number of curves to plot, you can select, I want 2 curves, not 1. So let's do 2. And generate automatic offset. That I don't know what it means. I usually just go with the default, but you can look into start those and maybe just a correct. I really don't know what it means. Coordinates of the axis. So I want 2 profiles. I want Faisal. Okay. So I want 2 profiles. The first profile, suppose I want it to be at 1 centimeter depth. Then the coordinate of the Y is going to be 0, but for the Z is going to be at 1. Okay? Because I want it at 1 centimeter depth. The Y, I want it across the central axis, or Y equals to 0. Okay? And the second profile, I want it to be support. We want something like around R50, so 4 centimeters. Let's select 3.5. Okay, so it puts 0 and 3.5. Okay, so now I have my profiles. This is the profile. Obviously, the black one is the one at 1 centimeter. Okay, and the red one is the one at 3.5. Actually, here on the legend, it has it there. Okay. So last thing is the dose XYZ show. So let's go back. So okay. So now we're gonna launch those XYZ show. Okay, and it tells you immediately this is the usage. Those XYZ show. It needs a density of dose file and density file. Density file is the X phantom, that file that we created, and it needs the dose file. So there we're going to select. Let's try see the one we generated now, bone, and the dose file also has the same name. Okay, so this is the application. Okay, and there it is. I start to, and you can see here the bone. Can you see it? That's where we have made our bone.
It's clear.
Okay, it's clear. And this you can change. I think there are options. Color. You can make it color wash. Of course, the statistics is bad. Okay, I need to run this for more histories. So 55 should be at I think the center of our phantom. So you can, I mean, so that's all for the XYZ. What I use it for is I use it the stat dose. I use that a lot. I don't look at those distributions. I look at profiles for a reason that will become obvious when we deal with BEAMnrc. Okay, so I'm going to stop here for the next bit. If there are any questions, please shoot.
Thank you, Dr. Omid. Any questions, please? Just raise up your hand and speak it out.
Yeah, go, Salim. Okay. And believe me, you're going to forget this. That's why when I give the assignments, try to do them. You're going to struggle. You're going to make mistakes. And that's why I wanted to try it. It's not going, probably it's not going to work the first time. If it did, you're lucky. For me personally, it did not work. Things did not work on the first time. But to be fair, I had to actually do the like manually edit the input files. We did not have at that time the graphical user interfaces. So please try to do these assignments. Try to be creative. Try to think of something and just try. I want to do this and run it and see the results. And if you cannot run it, if you have problems in the geometry, write it in the post it in the classroom, and then some people will help you with that.
Can we display as those 1, 2, 3, 4%?
You mean select the acidoses?
Blade, please speak. If you have the microphone on your side.
Here you mean this 5%? Actually, I noticed when I click on something, it actually gives me the value. That's something new because I don't use this application a lot.
Yeah.
So when I'm clicking on a certain voxel, it's giving me a value. Okay.
please how to open read dose distribution in GUI.
You can't. This is exactly what I was telling you.
Okay.
You need to use another application. It's the dose XYZ.
Okay.
And for plotting data, you need to use the stat dose. Otherwise, what you can do is read the manual and go and see, for example, what if you can decode this 3D file. If you can do that.
So basically, the stat dose, it comes with the MinW interface, or it's only for the Linux?
No, it's already installed. You should try it for Windows.
Okay.
So you try it with the CMD. The dose XYZ should also work, and you don't need to compile them.
Okay.
They should be compiled, ready.
Any questions?
So if you have Windows, just on the terminal, type stat dose.
Stat dose.
It should run. Or you type type dose XYZ _show. Also that one should work. Okay. So you type these commands when you are in the dose XYZ directory. Mm-hmm. Okay. Don't type it when you're in a different directory, because by default it scans the directory that you launch this application in, and it will see, do I have a 3D dose file or no? Okay.
Okay.
So if someone knows or can write a code for us that, you know, makes sense of these numbers, I mean, I would be very happy. You can actually contribute it to the guys from NRC, and they will really appreciate it. Although they have done it in a different way. That's why obviously people have fraud the stat dose and the dose XYZ applications. Mm-hmm. And this is a large file. It's see, these are numbers. Okay, so that's how it's done, and it's not an easy way with those XYZ. Not like those RZ. It automatically produces those plots.
Are you planning to show us City Phantom for the future?
I haven't done it before, but I can arrange to actually do it. So we will see with Bilal, we can create an anonymous patient. Yeah. Okay, you need to anonymize the patient, and let's see if we can actually create those XYZ from CT. You know, personally, I think it's tough because you're going to see, if you want to do heterogeneity corrections, you need to have information about your beam itself. So, for example, the MLC shapes and so on. So usually you want to actually calculate, you know, with 3D CT with CT, in based on your beam, your actual treatment plan. But there is an application called MMCTP. That's a McGill Monte Carlo treatment planning system, and basically the idea is you get your phantom, and then you have your Monte Carlo somewhere on computer. It will convert this, it will read the DICOM RT, convert and read the CT data, and then launch, actually reads the beam parameters, creates an input file for your beam, and sends everything to the EGS installed on a computer, run the simulation, and when the simulation is done, it will retrieve the results. You can get the dose distribution. It even has DVHs. It calculates DVH. This one does not calculate DVHs. The dose XYZ show, I don't think because it does not read the DICOM RT, the structure. It does not read that. This phantom is generated from dose XYZ.
Okay, now
but that is later on. Yeah.
Okay. People are asking private question. How can we get the MMCTP software?
Just type MMCTP and
it's
you can
free?
actually down. It's a it's
open
free.
source.
It's a GitHub.
Okay.
But I think I run it on a Mac. You have to. I mean, there are some structures, and I think there might be you can actually post questions, because when you want to launch something like this new, it's good to actually post questions. Okay, what should I do? You know, I tried this. Read the instructions carefully. There might be some prerequisite. I think you need a prerequisite software. But one thing you need to do, you need to have a dedicated Linux machine to do the simulations. Even if you're going to run MMCTP on a Windows machine, okay, you need to have a dedicated Linux machine to do the simulations. Otherwise, this is not going to be practical at all for you. You need a monster machine, and if you can have 2 machines or 3, does not matter. The more, because then what happens, MMCTP, suppose in a plan you have 2 or 3 beams. So what it will do, it will submit 1 beam on 1 machine, the second beam, second machine, third on the third one. And it will actually do the parallel processing for you, so that it collects gets the results as soon as possible. But that you cannot do until you do the beam. Okay, and this is probably, maybe I can start today a little bit on the beam, because it needs beam. You need a model. You need to model your linear accelerator with MMCTP. It's not going to do that for you. That's something you have to do independently.
I shared the link of the GitHub for the MMCTP.
Yeah.
Andrew Alexander, he's the guy.
Andrew Alexander. Yeah.
Andrew Alexander, yes. Okay, someone asking, where can I find the stat dose?
You want to find the application, or you want to launch it? Because if you want,
both.
Why do you want to know the location of the application? That's the guy we don't get.
So probably he would like to just launch it. How to launch it?
But if you want to know where it is, it's part of the. I mean, if you don't need that, why are you asking? But if you, it's actually the henhouse directory. So you go, okay, and there we have henhouse. There's a directory called Omega. Okay, that Omega is basically anything related to beam simulation. Those XYZ is part of the beam package. Okay, so BEAMnrc, and there is programs. So if you go into programs, okay, and you'll find there is those XYZ, and there is a stat dose. These are the GUIs. Okay, this is an important command. We're going to learn how to use this. And BeamDP is an application to analyze phase space files. Okay, but that's the location. But I don't know why you need the location so the stat dose is inside there. Okay, unless you want to modify something. Okay, and the file, how to launch it? You just type stat dose.
And he should be inside the root, right? To launch
inside. Yeah. So for example, I'm in home area now. So stat dose, it will launch from here. Okay, but reading, you see, I cannot read anything because it looks in the directory where I'm at.
Okay.
Are there 3D dose files or not? So there's nothing, right? So here, ls cannot access 3D dose files. No such file. So what you need to be in the dose XYZ. That's where you run your input,
where you have the dose files.
XYZ, yeah. And where you have the dose files. So now when you do stat dose here, unless you want to copy the files to somewhere else, that's a different story. But stat dose, okay. Now when I read, okay, the files that are available in this directory are listed there.
Any other questions before Dr. Omid moves to Beam?
EGS view is different. EGS view is similar to preview RZ. Remember in the RZ geometry? EGS view is used to use, do we have examples?
I think home.
X plus plus. It's in X plus plus. It's for X plus plus. It's I don't know if we have X plus. What do we have? Let's try this. Just I don't know if one of these where they are. I don't know if this is part of it or not, but let's see. The trash or what? Because I haven't done really X plus plus. That's why I rarely use it. Okay, maybe here. Okay, I really don't know where it is, or but that's an application to view geometries. X plus plus is an extension to X, where now you can actually have more complicated geometries. Okay, you can have spheres, you can have union of different geometries. You can model chambers very accurately with the X plus plus. But it does not have a graphical user interface. You need to go and create input files manually with a text editor. But of course, you put these numbers, you need a viewer, you need to see, does your geometry that you've entered in this, does it make sense or not? And I think the X view is the application to view the geometries that you have created in the X plus. Well, I'm not going to cover it now, but this is something later, maybe because I need to learn actually how to do that. I haven't done it before. I know Luqman actually knows a little bit about doing this. He might be willing to help us.
If we have more question for repinning, do we need to compile and run it again?
Compile what?
When you do repinning.
No, repinning it reads the data file, okay, and it just repins because we load this into the it repins everything in temporary. So if you want to, for example, plots to be done in a way or so on, that's up to you. But it doesn't. You don't need to compile. Compiling is when you create executable. This is a way just to manipulate the data that is stored in the memory.
Any more questions before we move on? Okay, Dr. Mohammed, go ahead.
Okay. I'll try to write an assignment for you for those XYZ, and I hope by this time a lot of people. I've counted actually. I got 7 replies out of 99. So I hope more actually reply. Either yes, you successfully did it, or you struggled, and then we can help you. Okay. The next application is a very exciting one. Okay, and I'm sure we're all going to have a lot of questions about it. There is a limitation with the those XYZ and those RZ geometries is if you want to model, for example, a linear accelerator or an X-ray tube. Can you represent the geometry of a linear accelerator with XYZ, or can you represent an X-ray tube with those RZ? Probably can't. So you need to write probably, or when you think of a linear accelerator, probably each region or each component of this linear accelerator probably needs a different geometry. Different thing, you can think about XYZ on top, and then we have an RZ below it, and then something else, and so on and so on. So a linear accelerator or an X-ray tube and machine. So it's a machine. So it also includes the collimator, everything, even until it reaches the patient. Each region from the source until your patient, for example, these regions will need a different geometry type or shape. So those X, Y, Z alone, we cannot do anything. Those are Z, we cannot do anything. The guys at EGSnrc, the developers of the code, they made actually a very nice tool to build such an accelerator. So the first thing you need to do is to think of the different regions in the accelerator. For example, we have a photon beam. The first thing we're going to have is a target. So a target, we can represent a target by a disk. Okay, a disk is enough. But now, after the target, we have the primary collimator. Okay, a disk cannot, we cannot use a disk to represent a primary collimator. We need something else. We have, for example, the flattening filter. Flattening filter, probably a disk cannot represent a flattening filter. Even you start thinking, okay, I'm going to stack disks with different radius above one another to generate this, is still not a good geometry. The jaws, we need a different shape, different component module, or different geometry to represent the jaws. The mirror, okay, the chamber. So that's why we need to actually, different regions in the linear accelerator, we need to define or have a different geometry. If you have your browsers, okay, this is the linear accelerator. This is, okay, you see this geometry probably the same, but now we have these scattering foils. I think this is an electron beam. Scattering foils. I don't know what is here. Monitor ionization. Oh, this is the ionization chamber. These are the accelerator vacuum. Okay, where are the scattering foils here? Not represented. Okay. But the geometries of each region is going to be different. Okay. So with BEAM, we have what's called component modules. So I'm going to show you, because I want to spend some time on this. The rest on the physics and so on, I think you all. Okay. This is source modules. Why is it always difficult for me to find stuff? Okay. Let's look at the component modules. I'm sure it's here. Oh yeah, here it is. It's in front of me. Okay, there it is. Component modules. Okay. So component modules is basically regions. I'm dividing. Think of this linear accelerator. I'm going to divide it into regions where I can represent each region with a certain geometry. Okay. So let's look at what's available. See, we have all of these regions. We have slabs, cones 3R, okay, and they tell you, okay, this is probably multiple slabs, arbitrary thickness, materials perpendicular, okay. This is designed to simulate cylindrical structures that can be described using a series of RZ points. I'm going to show you these things. The cone stack, that's another one, okay. Flat fill, probably this is from the name, it's proper flattening filters, okay. Chamber, jaws, dynamic jaws, that's a different component than the jaws, okay. Sync jaws, I think this is, I don't know which machine is that, this is called sync jaws. Dynamic jaws is probably the one for variant machines. Sync jaws, I'm not sure which one, okay. Applicat, that's for applicators, probably electron applicators, okay. Circular applicators, if you're doing stereotactic, you want, okay. Pyramids, block, MLCs, they have MLC, that's an old one, MLCQ. This is MLC, I think this is for variant machines. This is for probably Electa, you see Electa MLCs, okay. So this is the one, the variant. So this is the one where you can actually do IMRT and so on, dynamic. So this is model variant millennium MLC, yeah. Dynamic BEAMnrc. This is probably for Siemens. I'm not sure really, okay? Because I use only the ones that that I need. Mirror, X tube is if you have an X-ray tube, side tube, arch, CHEM is designed to model an arc-shaped array of ion chambers, such as those used in prototype tomotherapy unit. Okay. So they have a list of geometries that probably we can use. Okay. So now, when we go to each one, it shows you, it has some very nice explanation. So slabs, for example, okay, we have slabs of medium. I can put 5, 6, 3. But what's common is they all have the same radius. So this is the radius. So it's a disk, but all will have the same radius and they're stacked on top of one another. Okay, I cannot use slabs where I have different radius for this material and this material. So for example, scattering foils for electrons, this is probably not usable. Okay, unless you define, you actually have multiple slabs on top of one another. This is, I'm going to show you. Okay. In the old days, I needed to actually know how to write these. Cones 3R. Okay, it's different than the slabs. Now with this geometry, I can do something like this, where I have a medium inside this shape. This is, remember, it's a cylindrical symmetry. Okay, I have a medium inside and a medium outside. So which part of a linear accelerator probably will be useful to use this? The slab's probably a chamber or an exit window, probably that would be suitable. But what do you think this would be useful when in a linear accelerator? Which geometry in a linear, or part of a linear accelerator you think I can model using this geometry? Anyone knows? Flattening filter, maybe. Okay. There are limitations because some flattening filter you might have materials in the filter. So because here you're only limited to 2 medium. Okay. Which collimator? So this is probably useful to model the primary collimator. So the material inside is vacuum, and then the material here could be tungsten. This is something you get from the manufacturer, or you try to figure out what's the medium there, tungsten or lead, probably. Lead. I really don't know. But that is useful to model that geometry, okay? Where actually I don't need to have this fancy shape. I can just have one line just from here up to here. Okay, but I can make that cone shape, funny shape. Okay, so cone stack. This is probably, I can use this for scattering foils. Okay, because now, or flattening filter. Okay, but again, some flattening filters could not be modeled by a cone stack. But for scattering foils, maybe I can use this because I can think of the scattering foils. I don't know if you have seen how a scattering foil looks like, but some of them, they will have actually something in the middle with a larger thickness than we have like a pyramid shape or something like this. So this could be used for scattering foils. Okay, so we have to be careful, medium 1, medium 2, 3, 4, and we have to put the radius, min. These are parameters you need to actually define in the input file. That's why you think I'm going to use this, come to this figure and start to understand what these parameters mean. Okay. Flattening filter. That's why this thing, see, we have a medium surrounded by a different medium, surrounded by this geometry we could not do with a cone stack. So I think flattening filters for 6 MV, you can do it with the cone stack, cone 3 stack. But for 18 MV, this you cannot do. Okay, with that component module, you need the flattening filter component module. Okay, chamber. It looks something like this. I've never understood how this geometry works. I usually represent a chamber by 2 slabs with air in between, because I'm not really interested to record the dose of the chamber, but I want to just take the effect of attenuation and scattering from the chamber in the BEAM model. But you can actually make it fancy like that. Okay, chamber as phantom. This is a different way of using the component module, or it's the same chamber, but you use it as a phantom. I never used that, but some people, I'm sure they did. Okay, let's go down. The jaws, you see, that component module will allow me to do such a geometry. Something in between medium, and okay, and you can have an X jaw, and you have Y jaws, okay, below like this. Okay, so you can go through these, entertain yourself. Dynamic jaws. Yeah, dynamic jaws, I think that's variant also. So we have jaws, and then we have MLCs. Okay, this applicators. This is how an applicator looks like. This is how we can define them. Okay. Circular applicator. So you can have a circular applicator that looks like this. Pyramids. Could we use this to do physical wedges? I forgot really. Okay. What else do we have here? Blocks. That's for electrons probably, or for photons. Let's say circular tray. These are MLCs. That's the old MLC, component module. But let me show you how complex. So MLCQ, that's another one. So now we can actually have the shape. So the end looks something like not straight. Okay. So variant MLC. You can have the Tangen group also. Like, okay. And I think the MLCs, the ones that the inside, they have a different shape than what's outside, and it becomes a bit more complex than usual. Okay, what do we have else? MLC, that's elector, probably that's elector MLC. You see how the MLCs look like? Okay. And we have, what else? Yeah, this is the dynamic MLC. Let's see, we have 3 types of, these are MLCs in target, isocenter, target, isocenter, okay. And this is the full. So these are MLCs, shape of them. That's probably, if you have a variant machine, this is the MLCs that you should be using to do the modeling. Okay. So it's complex, you see. That's why we're going to have a lot of discussion on this. And so on. So what you need to do is you think of your linear accelerator, you divide the linear accelerator into different component modules, and then you build the accelerator. So I'm going to show you as an example what we're going to do. So we're going to start launch. Okay. Okay. So we're going to launch the BEAMnrc. Okay. And there, we're going to specify a new accelerator. Specify a new accelerator. These are the component modules that I have showed you in the file. Okay. So we have to visually think of divide the accelerator into these component modules, and we're going to put them on top of one another. I'm not talking about the dimensions. I'm not talking about the medium, the materials there. That's in an input file. But just think of what geometries we should use to actually represent linear accelerator. So I'm going to do something very simple, okay? I'm going to use the slabs. So I'm going to use that, and I'm going to call that, this is the target. Okay? So we're going to add, see now? So that's the first component model there. We can do the cones 3R. So we're going to do this, and I'm going to call this primary collimator. This is okay. Okay. What else? Flattening filter, I don't want to do it because the geometry is a bit complex. I want something quick. We're going to put the jaws. We're actually going to put slabs actually again. So I'm going to put slabs here again. So that I'm going to call it as something for the exit window. Doesn't matter. Okay. Then I'm just going to put the jaws. Oh, slab. Okay. Slab, slab. Okay, this is a problem. I don't like this, so I have to close it. I'll probably do it again. Okay, because we need to do this one time only. Specify new accelerator. Yes. Okay. So slabs, and that will be target. This is an identifier. You don't need to. We can't give it any name. And we said we're going to use this as that's the primary coordinator. We said we're going to skip the flattening filter. We need slabs again. So that will be the exit window. And then we're going to exit window. Let's do something. Chamber, we're going to skip that. Okay, I can put, I'm going to skip that. The chamber. We're going to put the jaws. So I'm going to select jaws. Just call this jaws. Okay. And probably I need another slab. So that will represent air. So air. Yeah. So air. Okay. You have to be creative in doing this. So these are, I think, these are the component models that's going to represent what I want to model, the beam that I want to model. So once we have done this, then what you need to do next is we execute. We need to, I think, save it. Save. Okay, I need to execute this and compile. So compilation is going to generate an executable. Those XYZ was an executable program. Those RZ was an executable program. Now is going to create an executable program where now is going to define the geometries, those geometries there for this executable program. It's for that particular beam. So when I click on compile, why I cannot save from here? What's wrong from here? I don't know why I cannot save this. It needs to be saved. But specify new accelerator. Oh, I remembered why. Okay, because I should actually click on save there. I should have done this. So let's do this quickly. Sorry for this target. Okay, add. Then we'll do this to be primary coordinator. Add. Then we said we need slabs again. That would be the exit window. Add. Then we need the jaws. Okay, and then we need this thing. This could be the exit from linac, or I'm just going to put it as air. So these are the 5 component modules. I need to do this, save and close. So we're going to save it, and we're going to, I'm going to put this as test, just call it test. And I'm going to use, I think I'm going to use this one because I have the materials that I need there. So now the component, the linear accelerator is actually, or the geometries, the stack geometries are saved for my accelerator. The next thing I need to do is to compile. And you need to do this only one time. So now it's compiling. Okay. Done. This part, the main, is just to the physics. This is the physics part, what I need, what's the source that I'm going to use, and so on. That we're going to deal with it later. But now I have these component modules where now I can start to edit them. Because you have vacuum and then you need air. Usually in linear accelerator, you have an exit window. It's not the one at the bottom. Okay. What does the other options during compilation imply? Most times we use optimize, I don't know. That's basically, usually it's the optimization level. So optimization 2 is usually what we use. Optimization level 3 is different. So that's something related to the compiler. Okay, I did not write the compilers. I don't know what they mean, but I know the EGS. Okay. So now with the slabs, we need to specify, for example, the layers. How many slabs do I have? A target could have one defined by one slab or 2 different materials. Okay, so suppose I want to put 2, and so let's put this to be 20. This is like a geometry, an outer geometry of the component module. So I want the component, it's not that dimension, but it's just that the halfway square boundary for the component module. Let's put here target. Okay, let's put tungsten. Okay, plus copper. All right. Distance of front of material in component model to reference plane. So now the reference plane is going to be where the beam is going to hit the target. So that is going to, so the distance is going to be 0, right? So because the target is there. And then define the layers. So now I have the slab thickness. Okay. Slab thickness, I don't know what thickness is used. I can put 2 millimeters. I don't know if that is correct or not, but let's put here, I can select from here tungsten, and then slab thickness 5. Depend, because you have to know the target thickness for the beam that you want to model. Okay. So material, copper, and click on OK. So now you can, nice thing about beam is for every component, you can preview it. Okay. So when I preview this, of course, this is a slab geometry. They have geometry, that means I have a slab with a certain thickness, and this is the second slab thickness, so 2 materials. Now I put here the slab be 20 centimeters. Do we have a target to be 20 centimeter radius? Maybe not. If you want to change it, you can change it. I don't think it makes a big difference, but let's change this into, for example, 1 centimeter. Okay. Still, the preview is going to be the same, but now the limit is going to be from -1 to 1. So that's the radius. Okay. So now we have finished actually defining the first slab, the target. Now we go to the next one. And that's why it's nice to have the figures. So outer boundary, this is probably, we're going to put 20 title. This is primary collimator. Distance. Now, the distance, of course, this is going to be next and below the target. One of the nice things I like about it is that it tells you, okay, the component module above it, where did it end? Remember, we had, I think the first was 2 millimeters and 7 millimeters. So I would say, okay, this is probably 0.7, or I can make it 1 centimeter. So maybe there is a gap between the target and the primary collimator. That doesn't matter, okay? That based on the geometry. The number of points to define the component module, probably 2. Okay. Now this, you need a piece of paper. You need to start to, or if my vendor was going to give you that dimension, that is fine. But here, basically, what is this stating is we have, so imagine this is the 0. So I need to define at this level a point as at z equals to 0, z0. I need to define a radius because I'm going to select 2. And then at z, so that the next z will be the height of the primary collimator. I'm going to define another z here. And then it's going to make, not, it's up to here only. Okay. Okay. So this will be medium 1, this region. It's a cone. Okay. And inside, I'm going to define it to be vacuum. So I'm just going to write something. I'm going to use some numbers. They don't represent a true linear, but just so that I show you. So let's put this to be 1. Of course, you can calculate this divergence if you want, like a 40 by 40 field at 10 cent at 100, or you can get it from your vendor. So z equals to 0, so that's 0. And radius, I'm going to put this to be 1, for example. And let's put this 3 centimeters. I'm going to put this 4. Okay. These dimensions are not correct. So I'm just showing you an example. You must have the same value. Closing, but not happy about it. Okay. This is now the material, the medium inside the cone. So there in a primary collimator, probably wanted to be vacuum. And outside, probably tungsten or lead. So let's put that. Okay. So view, Z min must have the same value as the first set of Z. Okay, let's look at Z min. Component module. I need to define the thickness. So what's here? 3 centimeters. So then we need to put here 3. Is that not working? 0 and R. Okay, number of points, just define points. Z min must have the same value as the first of the set of Z R points. Closing, but not happy about it. I really don't know what this means. Okay, let's try. Or is it the distance? Does it mean it's the distance from there? Maybe let's try it. Because it has been a long time since I used made my own. So let's put 1. R is 1. This is, we'll put this 4. Okay. So now it's happy about it. Okay. So this is the primary collimator. Okay. Where inside here we have vacuum, surrounded by vacuum, and then we have here we have this is a lid. Okay. Slabs. So exit window. Probably we need a beryllium exit window. I'm gonna put 20. Title window. So that's going to be at 4. Probably 1 is going to be enough. And thickness, I'm going to put 1 millimeter. And do I have beryllium here or mylar maybe or PMMA? Oh, beryllium, I have it there. Okay. Of course, this is a slab, so just no problem. Just 1 single piece. Okay. And then we come to this exit window. Okay, we come to this jaws. Okay, so jaws. Okay, so a number of jaw pairs, we have two, X and Y. Now the orientation, this is going to be, for example, the X jaw. I know I'm going quickly, but the material, what do you think the material is going to be? Tungsten. Okay. Now we have to think of what values we should use here. There is a quick way. So you can look at this figure and it will tell you what's the minimum, maximum, and so on. So what I'm going to do is probably I'm going to put the first jaw to be at 25 centimeter. So this is the front, that's on top, and probably the jaw thickness, maybe it's 9 centimeter. So we're going to put this at 34. And now for the Y jaw, I'm going to put half a centimeter in between. So this is going to be 34.5. Okay, and I have 9 centimeters, so 34 and 9, that is 45.9.5. What does this mean? Just look at the help. So this is the jaw. This is the distance from front window. So where is that distance from the source? Okay, so for me, I put for the X, that is 25. And the back jaw is the one here at the bottom. So that, since the jaw has a thickness of 9 centimeter, I assume 9 centimeter, then that is where it's going to be. And for the Y, it's going to be below the X. So I put half centimeter in between. Now here is where we control the divergence. So we can actually do it very quickly from here. So the lower edge, let's say I'm gonna put a -5 and 5, so that will get a 10 by 10 field applied to both jaws, and the SSD 100, 0. So what I'm telling this application is, okay, calculate for me where the jaws should be, such that I have a 10 by 10 field, because -5 to 5, that's okay, at 100 centimeter, and from the focal, the divergence we calculated from Z equals to 0. That's what it means. So it did calculate something for me there. Okay, these we're going to do next time. Preview. Okay, now that's my jaws. Okay, with the divergence that I have. Then the last thing is the slabs. I'm going to put this. That's air. So we're going to put okay, 1 centimeter. Distance there is 45.5. Probably this is not right, because I know for varied machines at least I know that this is about 35 to 100. So define layers. I'm going to put here slab thickness. We're going to put 30. And material. That material is, where is that? Preview. So it's just a single slab. Right. So I've entered these. Of course, when you do it, you have to be careful when you do this, especially when you do flattening filter. I'm going to save now the input parameter. Okay. So I'm in the directory called beam test, which I've collected this, and I'll put input one. Okay. You haven't. Okay. That's a pattern. That's not a problem. Okay. It's complaining because I did not define what's my source. A lot of things. But at least I want to save the geometry, because when you do the preview from here, it shows you now all the component modules stacked on top of one another. Okay. So here we have the target, we have the primary collimator, this is the exit window. Okay. This is the jaw. And now we have that. Of course, one thing that is wrong about this model is this should be air, this should be air and air, because the vacuum should only be here. But that is fixable. So here, basically the medium, any medium that you want to specify, I'm going to tell it, okay, use air, replace it with air. So now let's save. Okay, and then we preview. So that's fixed. Of course, now I have another problem because this part is not vacuum. This part should be vacuum. So you need to then go and fix the slabs and do something about it. Okay, but that's how you look at the beam model and fix things. Now, the next step is, of course, that's the main, in the edit main input parameters. It was complaining because I did not put the title. Okay, input 1. Okay, now again, we have the run options. First time, okay, phase space, this is the number of histories, maximum CPU, this we're going to change to 500. Let's check the physics because you all know this. So this one has to be exact. Let's set 2 on. Do I want to, okay, I'm going to leave the rest. Okay, so let's save. Okay, still complaining because I did not define my source. Now the next thing is, let's define a source. So if we're doing a beam accelerator, the source incident particle is going to be an electron, and the source number, probably, let's start with the easiest one, parallel beam from the front. So that's a parallel beam hitting the target, okay? The beam radius, I can put 0, I can put 1 millimeter, okay? This is 1 centimeter, so I'm gonna put 1. Again, these are the directional cosines, okay? So again, if you click on the help, this figure was not available in the dosxyznrc when you're selecting that option, but now, see, these are cosines, okay? So that's the beam. So what we want the beam to shoot in the positive X Z axis. So now we look at the cosines. This is 90 degree, because the beam is coming like that, is going to be perpendicular to the X and Y. So the cosine of 90 degree is 0, but it's going to be parallel to the positive Z axis. That's why we're putting here the cosine. This is asking the cosine. Kinetic energy, suppose this for a 6 MeV beam, 6 MeV photon, so we're going to put 6.0, okay? So that's fine, okay, and let's close, save, and let's try to run to see if so now the job has failed, it has failed. Okay, at least once more, I know why, okay? I wanted to run it, but without number of scoring planes, no phase space, okay. So let's run it just to make sure I don't have other errors. So I have to save it. Run, execute, okay. So once you see this 1, 2, 3, 4, 5, 6, okay, then you know that you're. So we have a linear accelerator model. Now, the important question now is what sort of output we want from this simulation. For those RZ, probably the output that we want is to those at different regions. For those XYZ, also those in different regions. But in beam simulation, you have to think what sort of output you want. One important output is called the phase space file. Okay? And that's basically, you want to collect what are that are reaching, for example, you want to collect all photons that are reaching them. Why is that important? Well, you can actually analyze the spectrum, get average energy or the spectrum of the beam, but you can use that collection of particles as an input for those calculations. Those are XYZ or those are Z. And this is probably you're going to spend a lot of time in doing that, because how we're going to make sure our linac is properly matches the linac in our department. You can't, because usually vendors will not give you the exact geometries. You will be lucky if you get them. So you have to start to tweak. You have to say, okay, maybe the energy of electrons is 6.1, maybe it's 6.05, maybe the beam actually is not 1 millimeter radius. Maybe it's 2 millimeter. Maybe it's something else, Gaussian distribution. And how you validate is then once you do the calculation of your beam and you do the calculation with those XYZ phantom, then you start to compare the PDDs and profiles to measure data. The more they match, then you're happy with the beam model. Okay. So I'm going to stop now. Okay, it's already 2 hours. I'm going to stop now. But we're going to go through this again. That's it. Yeah.
Thank you very much, Dr. Omid. Any questions before we conclude? I think everybody now is excited regarding the how to make the beam and how to make a linac based. There is a lot of things that should be done here, and I think we will spend most of the time working on this.
Yes.
So,
yes, one thing I really encourage you to do is you try to get, your beam model. So, for example, get jaws, get your collimator, what's the material, what are the distances. Okay, a lot of information you need actually to start. Don't ask me. Okay, I don't know this information. You need to get that information. Probably some other people will share this with you. But that is what you will need. And even if they give you actually that model of, let's say, a true beam model or another, or a linac or an electon machine, still the beam coming out from your linear accelerator might be different, a little bit different. And that's why you still need to do some tweaking, change the energies, check those XYZ, do the profiles and so on. So we're going to spend some time on the BEAMnrc. That's why I wanted to make sure you know that those XYZ, those RZ, because this is the most important, the most very interesting part. So try to get the information about your beams. Even if you have an X-ray tube you want to model, get the information about the X-ray tube. And probably next time, if you post this information, we will try to model it and create it. Okay.
Dr. Omid, what do you think that maybe let's say we have a collimator and then we play with the settings of the collimator. If we have the geometry, then we can at least have the drone with the collimator. Then we move to the target and so on. But I think starting from A to Z and make the linac the whole, it will take a huge amount of time.
Look, the primary collimator is not a big deal, because we can always say, look, the primary collimator, the maximum field size is 40 by 40. So I can select the dimension of the primary collimator to be something that, large, that's fine. What we need actually is, the material of it, probably. We need to also, where it is and its thickness. But the part that is really difficult,
target,
the flattening filter. Target is not really a big issue also, but the flattening filter, the design. This is why, if you notice, actually Varian, they don't provide you with the schematics of the parts that are up there. Now, what they do, they actually give you a phase space file.
Yes.
Think about it. They give you a phase space file where they have modeled their true beam machines, okay, and gave you a phase space file just before the jaws, because everything else below the jaws is something you can play with, but the rest above that is always fixed in a linear accelerator. So this is the tricky part.
Yeah, I think because it's a patent for them, they don't want to share their secrets with people. Otherwise, everybody will do the same.
Yeah. So if you have a cobalt unit, if you have a linear accelerator, Tomo, try to get that information, and we will try to do this. I have an old accelerator. Maybe next time I can show it to people, but you really need to start digging and get the schematics of your own linear accelerator.
We have 3 more questions before we conclude. Why we left E cut and B cut empty?
Because then it reads them from the it will then match the AE and AP from the PEX data file, unless you want to change it.
Sure. Okay. What's the difference between target and source?
they're different. So if you have electron beams, your source are going to be electrons. That's it. If you have a photon beam, your source is still electrons.
Yes.
Right?
Yeah.
But to generate the X-rays, you need the target.
Exactly.
Yeah.
And how to get profile and BDD.
We covered this, right? This is in those XYZ.
Yes.
Right?
Yes.
So I think you need to do a beam simulation, then a dose XYZ simulation, and then you get the profiles and the PDDs.
Any more questions before we conclude? Okay. Thank you everyone for attending, and thank you, Dr. Omid, for your valuable time.
Okay,
See you inshallah next time. Thank you very much.
Next week, inshallah. Okay.
Inshallah.
Yeah.
Bye-bye.